Okay, so now let's start getting into these radioisotopes and these decays. So if you haven't already, grab a periodic table so you have it in front of you so we know kind of what we're looking at and we can talk the same language. So you want to be able to look at the periodic table and look at atomic numbers and stuff like that. Okay, so I wanted to kind of look at these diagrams here first before we really get into those. So we talked about the alpha particle. So again, the alpha particle is the helium nucleus. Just a reminder, sometimes you'll see it written as He and sometimes you'll see it as alpha when you're looking at the equations. Beta particle, so I group these together usually. So this would be a beta positive and a beta negative. So I kind of put these two here together. So the beta particle produces, the beta negative produces a electron, beta positive produces a positron. I know some books and some people keep them separate, but really if you kind of understand what's going on, that's the main thing and knowing how to do that. Gamma radiation, we've talked about those. And neutrons and protons are the byproducts, so we're really not going to get into those in the great detail when we look at these decays. So I wanted to kind of go through and look at how we can detect these particles. And a lot of times we're doing with magnets, where we're producing an electric field between magnets. And what happens is gamma rays are unaffected. They just go straight. We cannot deter them. The alpha particle being positively charged. So remember, this is two protons, two neutrons. So the alpha particle is positively charged, wants to bend to the negative side. The beta particle is negatively charged, so it wants to bend to the negative side. Now, one thing you'll notice is the beta particle bends more. It's lighter. So it's easier to get it to curve than with the alpha particles. So let's go through and let's start looking at these decays here. So we have an alpha decay. So this is when an alpha particle is produced. And remember, alpha particle is two protons and two neutrons, the nucleus of the helium atom. So let's take uranium, 92, 238. So this is uranium 238. So sometimes you'll see it written as this. So we want to put the atomic number. We'll put the atomic number in the bottom. We'll put the atomic mass on the top. Now sometimes you'll see it written as, so sometimes you can see it like that. Sometimes you'll see it written on this side. They're all the same. The thing you got to remember is the smaller number is your atomic mass, or sorry, the atomic number, the number of protons, and then the bigger number is going to be your atomic mass. So let's take an alpha decay for uranium. So this is the uranium-238 isotope. And we want to produce, so I'm going to make some boxes here. We want to produce an alpha particle. So the first thing we're going to produce is a helium nucleus. So the helium nucleus has two protons and four particles in the nucleus, or atomic mass of 4. And then now it becomes math. So we want to kind of go through and do some math parts. So we have 238 here is equal to 4 plus x. Okay, so if I subtract 4 from both sides, I get 234. So that's what goes in here is 234. And then I want to do the same thing for the atomic numbers. I have 92 protons, gives me 2 plus something. So if I subtract 2 from this side, I have 90, so that gives me 90 protons. So now you want to go to your periodic table and you want to find the element that has the atomic number of 90, and you will see thorium, Th. And so this is how an alpha decay. So uranium-238 will decay to thorium-234. So if we're looking at this, you've got uranium-238, and that will decay to thorium-234. So that's your alpha decay. Well, but what about a beta decay? So again, we have positrons and neutrons. We'll look at the negative one. So we have a beta decay. And let's produce an electron. So it's going to be the same thing. Now again, beta particles are faster, they're lighter, they're smaller, so they're more dangerous typically. They're harder to block. So let's do, now not all of these are absolute good reactions. But let's look at this. Again, we'll have the 6 boxes here that we got to fill in. And you're like, well, how do I know what these boxes are? Remember, so a lot of these are going to be right here. So thorium, we have beta decay, so let's make it beta negative. So we're going to make an electron here with a -1 nucleus, or sorry, atomic number. So it has a -1 charge. And has 0 particles in the nucleus because it doesn't have a nucleus. So now if I add my numbers, I have 234 plus, or sorry, equals 0 plus something. So that's 234. And now this is where you have to be careful with the math. 90 is equal to -1 plus something. So I need to add 1. Make sure you're adding 1 to both sides. And I get 91 here. So I have a 91 there. And if you look at the periodic table, we have Pa on the periodic table for 91. Well, what happens if I'm doing the same reaction but with a positron? So I have thorium 234 yields a positron, so that's going to be a +1 and a 0. Take a second, you try it, and see what you're going to get. Okay, so I'm getting 234 here and an 89 here. So if you look at your periodic table, A, C. So that's going to be your beta decay. Now your gamma decay, so we're getting a gamma ray. A gamma ray has no mass, it has no charge, it's not even a particle, it's an energy bundle, it's light. So when we're looking at that, so if we look at the table that I gave you at the beginning, if we're looking at it, has 0 particles. So you're like, well, wait a second, nothing's really going to change. So let's use the thorium again, because it seems to be a popular choice that I've had today. So thorium, and I want to produce a gamma particle. So it's going to yield the same thing. I'm not going to get a different element here. So here's the difference is there's an asterisk here. So this is high energized or energetic or unstable thorium, and it releases that energy. So it's like a kid that's on Twinkies, it bounces around, it's got to release that energy. So that's what's happening here. So it's not as fun. It's not a great, beautiful chemistry reaction. It's an energy reaction where it's releasing a lot of its energy. So and what's interesting is what we're going to look at, and what a lot of you will be doing in your lifetime is you're dealing with these. If you're going into, let's see, radiation therapy, or if you're going into things like that, if you're doing X-rays, any of that stuff, you're going to see a lot of this stuff in your careers. Unfortunately, some of you will see it in your life. If you ever have cancer, have relatives have cancer, you're going to see a lot of these things. So I want to kind of go through and talk next about this radiation. So these are your decays, these are your reactions. And so we know some of them are dangerous. We know most of the radiation that you're ever going to be exposed to will happen naturally. Actually, bricks and houses give off radiation. Radon, if you've ever, I know where I grew up in the north, we have basements. You have to do radon detections in your basements because radon can build up in the basements from decay in the soils. So there's natural radioactivity that's happening around everywhere. And probably, some people say anywhere from 75 to 85% of the radiation you're exposed to is a natural form of radiation. Now, X-rays and other forms will fill up the other things. If you live near a nuclear plant, then you will have potential exposure to other nuclear radiation. So what we want to do next is how much is too much radiation, and then how can we detect it? So that's where we want to go in the next videos. We want to look at how much is too much and how can we detect these radiations.